In this lesson, we are going to introduce ourselves to limits of functions of two variables and how to prove whether or not the limits of these functions exist. Now let's assume that f is a function of two variables whose domain D includes points which are arbitrarily close to the point AB. Then we say that the limits of the function f of x, y as x, y approaches a, b is equal to L. Now let's try some examples. Let's say we want to find the limit of the function 3x squared plus 1 divided by 2y, where x, y approaches 1, 2. Now in this case, let's try and see whether direct substitution is going to work. Now you realize that we have x to be 1 and then y to be 2. So long as we can plug in y here so that the denominator does not go to 0, it means we can use direct substitution. Now since y is equal to 2, 2 times 2 is 4. Therefore, we can proceed and then use direct substitution. So we are going to plug in 1 for x and then 2 for y. So we have 3 times 1 square plus 1 divided by 2 times 2. And we have this to be 1 squared is 1 times 3 is still 3. So 3 plus 1 divided by 2 times 2 is 4. This becomes 4 divided by 4. And then we have this to be equal to 1. Therefore, the limit of this function as x, y approaches 1, 2 is equal to 1. Now let's take another example where direct substitution does not really work. So we want to take the limit of the function x minus y over y squared minus x squared, where x, y approaches 1, 1. So let's try direct substitution. So here we have 1 minus 1 divided by 1 square minus 1 square. So this becomes 0 divided by 0, and this is indeterminate. We don't actually know what this value is equal to. Now since this is indeterminate, it means that direct substitution does not really work here. So let's try to do factorization. Now we have this to be difference of two squares, so we can work out this. We can try to manipulate the denominator. So we can express this limit as we have the limits of the function x minus y divided by, here we can express this as y minus x times y plus x, and we have x, y approaching 1, 1. Now notice that x minus y is not the same as y minus x. Now at the numerator we have x minus y, and then we can further express this or represent this as, so negative y comes in front and then we have plus x, and then we factor out negative 1. Now negative 1 times what will give you negative y, that is y, and then negative 1 times what will give you positive x, so that is negative x. So instead of having x minus y, we are going to have negative 1 into brackets y minus x. So we have this to be equal to the limit as x, y approaches 1, 1 of the function negative 1 into brackets y minus x divided by y minus x times y plus x. At this point, you can cancel out y minus x, and then we do direct substitution. So we have negative 1 on top divided by y is 1, x is also 1, so 1 plus 1, and that is equal to negative 1 over 2. Therefore, the limit of this function as x, y approaches 1, 1 is equal to negative 1 over 2. Now we can have cases where neither of the two methods work. That is, we can have a situation where direct substitution does not work and then method of factorization also does not work. Now in such a case, how do we prove whether or not the limits of the function exist? And even if they exist, how do we find the actual limits of the function? So remember in calculus 1, in calculus 1, we defined the limit of a single variable function as the limit of the function f of x as x approaches a is equal to L. Now, with functions of single variables, we had only two directions in approaching a. That is, we could either approach a from the left hand side or from the right hand side. So usually what we did was to find the left hand limit, and thus we say that if the left hand limit, which is given by the limit of the function f of x as x approaches a from the left, is equal to L1, and the limit of the function f of x as x approaches a from the right is equal to L2. And then we continued to say that if the left hand limit was equal to the right hand limit, then the limit of the function f of x existed. And then on the other hand, if the left hand limit was not equal to the right hand limit, then the limit of the function f of x did not exist or does not exist. So for functions of only one variable, we had only two directions in approaching a, either from the left hand side or from the right hand side. Now we are going to carry this same idea to functions of two variables. Now the only difference is that with functions of two variables, we have infinitely many directions in approaching the point AB. So let's assume that we have the limit of a function f of xy where x comma y approaches a comma b along path A, and let's call this L1, and we have the limit of the function f of x comma y as x comma y approaches a comma b, this time along path B, is also equal to L2. Now because we have infinitely many directions in approaching the point AB for a function of two variables, what we just need to do is to find two limits for two directions which are not the same. What we need to do is to find two limits of two directions or from two directions which are not the same. Now, so long as L1, which is the limit of the function as x comma y approaches AB along path A, is not equal to the limit of the function where x comma y approaches a comma b along path B, then we say that the limit of the function f of x comma y does not exist. So as I said earlier, because we have infinitely many directions in approaching the point AB, what we just need to do is to find two different limits for two different directions which are not the same. So long as the limit along a certain path is not equal to the limit along another path, then we say that the limit of the function does not exist. Now in other cases, you can come across a situation where the limit L1 is equal to the limit L2. Now in this case, it does not necessarily mean that since L1 is equal to L2, the limit of the function exists and is equal to the value of L1 and L2. Now, the reason being that since we have infinitely many directions in approaching the point AB, approaching AB from only two directions are not sufficient to confirm the limits of the function. Even approaching the point AB from 5 directions are still not enough. Even for 10 directions are still not enough because we have infinitely many directions in approaching the point AB. But even with that, there are at least 5 paths that we usually work with. So we usually have 5 paths that we usually work with or work along. So these are along the x-axis. So usually we want to do along the x-axis, and then we also do along the y-axis, and then thirdly probably along the line y is equal to x, and then probably along the parabola y is equal to x squared, and then lastly let's say we have x equals y squared. So along the parabola x equals y squared. So even if 1, 2, 3, 4 give the same results, however 5 gives a different results, then it means that the limit of that function does not exist. Even if all 5 produce the same results, it still does not confirm that the limit of the function exists and is equal to the values that we are obtaining. We can only confirm the limits of these functions using what we call the delta-epsilon definition of limits, and this we are going to discuss in the next lesson. But even before that, let's try some examples. So for example 1, we are going to show whether or not the limit of this function as x comma y approaches 0, 0 exists. Now let's try to solve this example together. Now the first thing we need to know or understand is that direct substitution and then method of factorization is not going to work for this function. So what we need to do is to find the limits along two different directions, such that if the limits along both directions are not the same, are not equal, then we basically conclude that the limit of this function does not exist. So we basically need to find the limits along two different directions, and if they are not equal, then the limit of this function does not exist. So first of all, we are going to let f of x, y be equal to the function given, which is x squared minus y squared divided by x squared plus y squared. The next thing is we are going to approach the point 0, 0 along the x-axis. So that is the first direction we are going to look at. We are going to approach the point 0, 0 along the x-axis. Now along the x-axis, y is equal to 0. So let's say if you take the xy plane, this is y, this is x. Along this line, we have y to be 0. So let's say we can select a point here, that is 1, 0. We can select another point, 2, 0, and so on and so forth. Along this line, y is equal to 0. So for f of x, y, we have this to be f of x 0, because y is equal to 0, and that is equal to, now wherever we see y in this function, we are going to plug in 0. So we are going to have x squared minus 0 squared divided by x squared plus 0 squared, and that is equal to, this becomes x squared divided by x squared, and that is equal to 1, provided that x is not equal to 0. Now if x is equal to 0, this becomes indeterminate, and then we don't know which value it is. So along the x-axis, we have the limit to be equal to 1. Therefore, we say that the limit of the function f of x comma y as x comma y approaches the point 0, 0 along the x-axis is equal to L1, and that is equal to 1. Again, we are going to approach the point 0, 0 along another direction, so along this time the y-axis. Also on the y-axis, we have x to be equal to 0. Along this line, x is equal to 0. So for f of x comma y, that is equal to f of 0 y, and that is equal to, now from this function, wherever we see x, we are going to plug in 0. So we have 0 square minus y square divided by 0 square plus y square, and that is equal to negative y square over y square, and this cancels out this, and then we are left with negative 1. That is provided that y is not equal to 0. If y is equal to 0, this becomes indeterminate. So we say that along the y-axis, we have the limit to be equal to negative 1. Therefore, the limit of the function f of x comma y as x comma y approaches 0 0 along the y-axis, which is equal to L2, is equal to negative 1. Now in this case, since L1 is not equal to L2, it follows that the limit of the function given does not exist. Since L1 is not equal to L2, it follows that the limit of the function given does not exist. Now let's move on to the second example. So for the second example, if f of xy is equal to xy over x squared plus y squared, does the limit of the function given as xy approaches 0 0 exist? That is our question. Again, let's try to solve this together. So as usual, we need to find the limits from two different directions. If they are not the same, then we basically conclude that the limit of the function does not exist. So first, we are going to let f of x comma y be equal to the function given, that is xy divided by x squared plus y squared. Then we approach 0 0 along the x-axis, and we know along the x-axis y is equal to 0. Therefore we have f of x comma y, that is equal to f of x 0. So wherever we see y, we are going to plug in 0. So we have x times 0 divided by x squared plus 0 squared. Now this is equal to 0 divided by x squared, and this is equal to 0. That is provided x is not equal to 0. So along the x-axis, we have the limit to be equal to 0. So the limit of the function as x comma y approaches 0 0 along the x-axis, which is equal to L1, is equal to 0. Now let's move on to the second direction. So here we are going to approach the point 0 0 along the y-axis. Along the y-axis, we have x to be equal to 0. Therefore we have f of x comma y, and that is equal to f of 0 y equals, wherever we see x, we are going to substitute 0. So we have 0 times y divided by 0 square plus y square. This is equal to 0 divided by divided by y square, and that is also equal to 0, provided that y is not equal to 0. So we say that the limits of the function given as x comma y approaches 0, 0, this time along the y-axis, which is equal to L2, is also equal to 0. Now here we have L1 to be 0, L2 also to be 0, but this does not necessarily mean that the limits of the function exist and is equal to 0. We need to also check for another direction. So we are going to consider the direction y is equal to x. So we are going to approach 0, 0 along the line y is equal to x. So with that, we have f of x comma y equals, so first of all, the function f of xy is equal to x times y is equal to x times y divided by x square plus y square. Let me check if I'm correct. So xy over x square plus y square. So that is exactly what I have here. So here we are going to have y equals x. So this is equal to f of x, and then y is equal to x. So xx. So wherever we see y, we are going to substitute that for x. So we have x times x divided by x square plus x square. Now this is equal to x square on top divided by, this is 2x square. So this goes here once, this goes here once. So we have 1 over 2. That is provided that x is not equal to 0. As usual, if x is equal to 0, the numerator becomes 0, the denominator becomes 0, and this is indeterminate. So along y equals x, you realize that we have the limit to be 1 over 2. Therefore, we write that the limits of the function as x comma y approaches 0, 0 along the line y equals x, which is equal to L3, is equal to 1 over 2. Therefore, since L1 is equal to L2 and that's not equal to L3, it follows that the limit of the function does not exist. Now in all two examples, you realize that the limits of the functions did not exist. So in a case where the limits of the function existed, how do we find them? And that is what we are going to focus on in the next video, where we treat the delta epsilon definition of limits. That's it for today's video. Thanks for watching, and see you in my next video. Bye bye.